Hello there, and welcome to this installation in our mini series on the elevation factor. In this video, we're going to discuss the elevation factor itself, see how well it performs. My name is Tom Meyer, and here's the notation for the formulas that we have developed up to this point. I put this up here for your reference. Likewise, here's the formula for the north-south radius of curvature. Here's the east-west radius of curvature, and that's the Gaussian radius of curvature. We have spent a lot of time discussing the formula for the elevation factor, focusing up to this point on the radius. Right now, we'll turn our attention to the height. The height is a geodetic or an ellipsoid height. Geodetic and ellipsoid height means the same thing. And one would typically get this from a GPS GNSS unit, but if you're doing trig heighting with a total station traverse or running levels through the stations, you can get H that way as well. Now, it's quite possible that you might have an orthometric height instead of an ellipsoid height, and in theory, it really should be an ellipsoid height, but it doesn't make any practical difference. The ellipsoid heights can't be more different from an orthometric height than 30 meters in the conterminous US. And so tacking on plus or minus 30 meters to H doesn't make a practical difference in the answer. Because H is so much smaller than R is going to be on the order of 6 million meters. H is probably in the hundreds, could be in the thousands, but it's always going to be so much smaller than R. Then plus or minus 30 meters on H just isn't going to make a practical difference. So if we're using the state plane coordinate system of 83, we have a value for R that is actually a constant, and it's 6,372 kilometers. If we're using state plane 22, then we're going to use the Gaussian radius of curvature that we've developed in the previous videos. It might be interesting to know at what latitude does the Gaussian radius of curvature for GRS 80 match 6,372,000 meters, and that works out to 36.7177 degrees north. That is the horizontal blue line that you see in the map off to the right. It's near the center of the United States, but it's not actually in the center. It's shifted a little bit to the south. Here's our formula for reducing distances observed at height. You just multiply the distance by the elevation factor, and that gives you the corresponding distance on the ellipsoid. So at this point, we have everything that we need to do some testing. Let's give ourselves some parameters to explore. We'll start by considering a baseline on the ellipsoid that's 1,000 meters long, and we'll hold that as a constant. 1,000 meters is a very long line for a surveyor. It's over 3,000 feet. And the reason that number is chosen is that it's the longer the baseline, the less well our reduction will probably work. Because after all, we are approximating an arc with a straight line. And so that's the same thing as substituting a chord for the arc, the corresponding arc. Well, that substitution is going to break down the longer that the arc is. And so picking a value for the distance that's well outside normal practice is sensible. And 1,000 meters is a number that we see in the literature, so it's a fairly typical testing value. It's long enough that if it works well for 1,000 meters, it's going to work that much better for the lines that we work with on a regular basis. For the latitudinal values, let's go from 20 degrees north to 71.25 north. That's south of Hawaii to the North Shore of Alaska. For heights, let's go from negative 250 meters to 2,000 meters. I believe negative 250 is below everywhere in the United States, so that's safe. And I'll justify my choice of 2,000 meters on the next slide. For azimuth, let's do let's consider lines that are running due north to 0 degrees, 45 degrees, and 90 degrees due east. There's no reason to consider the other quadrants because the azimuth is symmetrical around those values. If we create a plot of the population of the 30 most populous U.S. cities against their elevation, we see that by far and away most of them are at 1,000 feet or less, and just a few very high cities like Albuquerque, Denver, Colorado Springs, they're up at around 6,000 feet or a mile. Denver is known as the Mile High City. All of these are less than 2,000 meters. So 2,000 meters is conservative in that sense. Now, certainly, there's plenty of places in the mountainous regions of the U.S. that are well over 2,000 meters high, but there are no major population centers higher than 6,000 feet. So it seems prudent to consider values where people are going to work most of the time, rather than thinking about how well does this reduction work up in the collegiate peaks of Colorado, where we're probably not actually really going to use it. All right, so here's the mental model to refresh our memories. This is what we're doing. We are going to observe a slope distance d sub s. Then somehow we're going to turn that into a corresponding horizontal distance d sub h, which in this picture is a circular arc. Then we're going to reduce that circular arc to a corresponding circular arc on the reference ellipsoid whose length is d sub e. There's ambiguity exactly how do we convert or approximate d sub h, how do we convert d sub s to d sub h? I'll speak more about this in the summary, but for now I'm going to set the ellipsoid heights of our two stations to be equal. So h sub a will equal h sub b, and therefore d sub h is approximately d sub s. We'll be just substituting we'll substitute the chord for the arc, and d sub s will be the straight line distance between a and b. Here is the algorithm for the testing. So with the parameters that we've just discussed, we have our point A, we've got the latitude and the longitude for A. The longitude, it doesn't matter, it doesn't enter into any of the formulas. We have a testing height H, we have our baseline on the ellipsoid D sub 0, and we have a set of three azimuths to work with. Now, since we're given A, I will use the direct problem of geodesics on the ellipsoid to determine the coordinates for B. Then I will set the ellipsoid heights of A and B equal to the testing height of H, which you remember is going to go from minus 250 to 2,000 meters, and I'll do it in steps of 250 meters. Now that I have A and B in BLH coordinates, latitude, longitude, height, I will transform those into Earth-centered, Earth-fixed XYZ coordinates. These are Cartesian, three-dimensional Cartesian coordinates. So then I calculate the slope distance between them just simply using the three-dimensional form of Pythagoras' formula. That's the square root of the change in the x squared plus the change in the y squared plus the change in the z squared. Next, for state plane 22, we will compute the Gaussian radius of curvature as shown in previous slides. And I'll do it at the mean latitude between A and B. I also tested this at the latitude of A only and the latitude of B only, and it doesn't make any difference. So doing it at the average is fine. Then we are going to compute the elevation factor, which again for state plane 22 is the Gaussian radius of curvature divided by the Gaussian radius of curvature plus h. Or for state plane 83, it's the constant value of r plus the constant value of r plus h. Finally, we'll compute the reduced distance d sub e, and that's just the slope distance times the elevation factor. Finally, the error will be d sub e minus d sub 0 Remember that the goal is to always reduce d sub e to the ellipsoid. So in every case, the reduced distance d sub e should, in an ideal world, it would equal 1,000 meters exactly. So let's see what happens. With this test suite, we have 1,500 values on this meridianal band. The average error was 0.0008 millimeters. It's extremely accurate reduction. And this is on a pretty long line, on a 1,000-meter line. That's extremely good. Excuse me. The standard deviation of the 1,500 samples is a little bit more than 1/4 of a millimeter. So this is a highly reliable reduction. This approximation works very, very well. It's not perfectly symmetrical. The most probable value is just slightly negative, just slightly. And this is caused by our approximation of a chord, we're approximating an arc with a chord, and the chords are always slightly shorter than the arcs. So the average value is just a little bit negative. It's not quite as good for 83. Of course, the Gaussian radius of curvature is a function of latitude, so it is adapting its value for whatever latitude we're working at. But in state plane 83, the value for r is a constant, so it fits well at the latitude that it matches the Gaussian radius of curvature, and it's not as good elsewhere. Here, the most probable value, the mean of the sample set, is a negative 0.14 millimeters. This is still extremely good. We've been using the state plane 83 system for 47 years without any problems. It works extremely well, but it's not as good. These results are not as good as what we see for the new state plane 2022. The standard deviation is 0.4 millimeters. Not quite twice the size of for 22. And here we see that there's errors that are exceeding a millimeter in the extremes. The distribution is not very symmetric. It's skewed towards this to the negative. Those are southern values. And this is a consequence of the radii of curvature, M and N, changing fastest and being the most different towards the equator. All right, so in short, the elevation factor is a very good approximation. It's going to reduce our slope distances down to the ellipsoid effectively, but it also might be interesting to take a look at the winners and the losers. So let's see, where was the performance the best and where was it worst for the state plane 2022 method using Gaussian radius of curvature? So it worked the best, just so happens, at 24 degrees, 11 minutes, 1 second north, with a height of 1,750 meters, not quite the highest. The azimuth was 45 degrees, and the error was 8 times 10 to the minus 6, which is diddly dot squat, effectively perfect. I could anticipate that the azimuth would be 45 degrees. The Gaussian radius of curvature is the mean of the north-south and east-west curvatures, and so it's going to be a good match for the radius of curvature in the normal section around 45 degrees. So that makes sense. I would not have anticipated H at 1750. I would have thought it should have been on the ellipsoid or closer to it, but it wasn't. Just so happens. So the Gaussian radius of curvature is not an exact fit for the radius of curvature of the normal section, and apparently this means that H at that particular place shouldn't be 0. That's just the way it worked out. 24 degrees, wouldn't have anticipated there or anywhere else. It wouldn't be clear to me where this should have been performing the best. Perhaps I would have guessed further north than that, but No, that's the way it worked out. But for the worst performing locations, this was predictable. For the worst positive error, it's at our southernmost boundary, 20 degrees. At the maximum height, 2,000 meters, running north and south, and the error is 0.9 meters. All of that is entirely anticipatable. And for the worst negative performance, it's at exactly the same place, but running east and west instead of north and south. Completely anticipatable. So what about 83? Works out that the best location is 49 degrees, 17 minutes, 9 seconds at a height of negative 250 meters, azimuth of 90 degrees due east, and the error is 2 times 10 to the minus fifth. In other words, again, diddly dot squat. I think it's a pure coincidence that the best place works out to be the northern border of the United States between the US and Canada. I think it's extremely far-fetched to believe that James Stem chose the value for R so that that would be the case. It would be a pretty challenging computational feat to perform to figure out what that value is, but it's not impossible. And in the time that he was working these numbers out, we certainly had computers that could do it. You could write a Fortran program to do this. But why would you? Why would you want to set the best performing location on the border with Canada? Canada doesn't use State Plane 83. So I think that's just a coincidence, but I think it's an interesting coincidence. I would have guessed that H would have been 0 instead of negative 250, but turns out it wasn't. Once again, the worst performing in terms of the positive is completely predictable. It's at 20 degrees south, or 20 degrees north, height at 2,000 meters, azimuth of 0. Everything's the same as with 22. But the worst, interestingly enough, is not. It was at 71 degrees north, 15 minutes. No idea why it would work out that the worst negative would be so far north. The other numbers are anticipatable, but the latitude being not 20, that took me by surprise. But that's the way it worked out. So the values for State Plane 22 are more anticipatable because it's pretty easy to see how the Gaussian radius of curvature is matching up with the north-south and east-west radius of curvatures. But that's just not the case with 83. We're using a value that's fit best to the middle of the United States. And how that's going to match up with M&M, well, this is how it matched up. It's hard to anticipate. All right, so in summary, when we're computing state plane coordinates and we're doing this reduction, the error that we're going to get in our final coordinates will not be dominated by this reduction. It's quite the opposite. This reduction is not going to be introducing probably even a single millimeter. Remember that the results that I showed you here were for a line that was 1,000 meters long. For the sorts of lines that surveyors use, hundreds of meters maybe, usually less, the error is going to be far, far less than a millimeter. And so the uncertainty that we're getting out of our instrumentation, like the fixed uncertainty in the parts per million with an EDM, that is certainly going to dominate the error in the state plane coordinates. So we can just say that the elevation factor just works. The next thing to think about is, well, our mental model is that we're reducing a horizontal distance at height down to the ellipsoid. And in this error analysis, I set the ellipsoid height equal at both stations. But what if that's not the case? What if we're working in a mountainous place where the height of the two stations is really quite different? then what value should we use for d sub h? Well, one choice is just use the horizontal distance from the observation station. Arguably, that value doesn't match the mental model very well, but it will always be available, assuming that we're running a total station traverse. Another good choice would be to take the average of reciprocally observed horizontal distances. Suppose we're running a control survey. We would hopefully observe all of the lines forwards and backwards, so we'll have all these reciprocally observed distances. That would be best practice in any case. And it seems like that is a good match to theory, but if we're not doing that, if we're not reciprocally observing the horizontal distances, then, well, it wouldn't be available. One could just use the slope distance. That would always be available as well, but it might not be a good match to the mental model that we're using. And so, since the slope distance is always available and it's unambiguous, horizontal distances, the horizontal distance from A to B doesn't equal the horizontal distance from B to A. The slope distance is not ambiguous. It's clear exactly what it means. So this makes us wonder, well, would it be possible to reduce slope distances directly without using the elevation factor and do it rigorously? And the answer is yes. And that will be the subject of our final video. The next video will discuss exactly that. All right. So thanks for watching. We'll see you in the next one.